Our next speaker is Andreas Spillner,
Yeah.
speaking on computing phylogenetic diversity for split systems.
Yeah, thanks, Charles, for giving a nice introduction to the basic problem. Because now we're going back to the basic problem. We don't want to select regions, but really individual species. So it's really now about, again, selecting among all k-element subsets of a set of n species, one k-element subset with high diversity. And this is joint work with Bin, our PhD student, and Vincent. And, well, I mean, as Charles mentioned in his talk, if you look at this problem on a phylogenetic tree, this problem has been solved some years ago. So what we tried to do was to generalize it for situations where the evolutionary history of the species under consideration is not well represented by a single tree, but could be represented better, say, by a network, for example. So let me just give you a brief outline of my talk first. After giving some definitions and, a little bit of motivation, I will again focus on the theory side, which is computational complexity. So this is quite a good session where we just focus on the theory side and less on biology, I guess. Okay, this is what we've seen in the previous talk by Charles. The diversity of a subset with respect to a given phylogenetic tree on a given set of taxa is just the length of the shortest tree connecting this set of taxa. So, well, that's it, more or less. So if you now look at a network, and to be more precise, this is what is usually called a split network, then you could also look at the subset, those circular taxa, and again, the diversity of the subset is the length of the shortest tree connecting those taxa in the network. Please note the slight difference in the definition. It's now because there might not be only a single one. There can be many different trees of the same length, or of shortest length, of course, but they all connect up the given set of taxa, in this case, these four circular taxa. So, and as I said, this is a split network, which is usually just a tool or just a way to represent or to visualize sets of splits which are possibly incompatible. I mean, if they are compatible, they fit on a tree, you just have a phylogenetic tree for your set of taxa. But this generalizes the situation to, in the sense that you can have incompatibilities in your splits. And then you use this kind of network to display it. And as we've seen in, I guess, at least once, for example, in Daniel's talk about this network and tree visualization tools, we have splits represented by families of parallel edges in the network. So, for example, these, where's the rod? These three edges represent one split which separates x5, x6, and x7 from the rest of the taxa. And the length of these edges, they all have the same length, they all have parallel. The length of this edge is just the weight of the split, just as the branch length in a tree would be the weight of the corresponding split in a phylogenetic tree. And now, as you can see, the weight of this split contributes to the PD score of the subset if and only if there is an edge in the tree which actually crosses this split. So one of the dotted edges should be red, and it is, of course, in this particular case. So having this in mind, it's not too complicated to generalize this definition of phylogenetic diversity with respect to a tree, which was given by Faith in '92, to this more general situation where we're just given a set of splits. And, well, this is an ugly slide, no picture on it, but yeah. Okay, you're just given a set of splits of your given set of taxa. And then for each of the splits in this split system, you have a non-negative weight. And then for a subset of your taxa, you would like to define what is the phylogenetic diversity of this subset with respect to this weighted split system. And this is the way you can do it. You just sum up the weights of all those splits which separate at least two taxa in your subset. And this is more or less the formalization of what we've seen on the previous slide with respect to this particular network. Okay, now we have defined what the phylogenetic diversity of subset with respect to a split system is. yeah, and then we can go for the basic problem, trying to optimize or try to find subsets of a given cardinality that maximize phylogenetic diversity. And first of all, I mean, I already gave you some kind of motivation by saying, okay, if you want to find subsets of high diversity with respect to a network, then this is one way you could go. And I also want to show you another situation where this kind of problem arises, or that can be phrased in terms of split systems and phylogenetic diversity with respect to split systems. And if you don't compress the information you have into a network, but just say you have a collection of trees, say phylogenetic trees derived from different regions of the genome, on one and the same set of taxa, so you have different phylogenetic trees, and then if you look at a subset, say these two, and on both trees it's the same three-element subset of the taxa, and on both trees then you have, according to this very original definition, just the length of the red tree, which is the diversity of the subset with respect to this individual tree. But if you have several trees, then you could try to average this out on this collection of trees, and in the end this just means that you sum up the lengths of these red trees. And then of course you could try to find a subset, say a three-element subset, such that the sum of the red tree lengths is as big as possible. And this can too be phrased in terms of split systems. You just take all the splits from all the trees and put them into one big split system. And the only thing you need to be aware of is that, well, there could be splits which appear in more than one of these trees. And in this case, yeah, you just have this split once, of course, in your split system because it's just a set of splits. And then you need to adjust the weight of this split. It's then just the length of this branch plus the length of this branch gives you the weight of this split. So in this sense, if you want to average out over several trees or just look at the split system, it's more or less the same thing. Okay, so this is more or less like, yeah, motivation that, I mean, there are other problems as well, but I won't want to go into details right in this talk, but I mean, there are other problems as well that can be phrased in terms of phylogenetic diversity with respect to split systems. So it's kind of a general framework you can think of, and it gives you some kind of, yeah, way to access all these different problems, and it gives you some feeling where actually the difficulty, the complexity with respect to computation and finding optimal solution lies. Okay, so let's move on to the next part. And as you might have guessed already, the general problem is hard. I mean, it's hard in different ways, and I just want to, yeah, give you an intuition why. By showing it's NP hard. I mean, you could ask more questions, just as Charles did, about approximation, about parameters, so that you can restrict the structure of your problem, try to find out whether it's tractable if it has a very special structure. I will come back to this later on. But the very basic idea to showing hardness is that you reduce from some graph problems, and there's a very close connection. So given a just graph with edges and vertices, you can associate to it a split system. And this works as follows in a very simple way. For every edge in the graph with endpoints A and B, you form a split, and the underlying set you split is the set of the vertices of the graph. And you just split out the two endpoints of the edge versus all the other vertices in the graph. So this is the way you associate to a graph a split system, and all the splits get unit weights. You don't even need the full generality of the problem. And yeah, and then, I mean, I don't want to give a formal proof. It's just to give you an intuition what's going on. If you then look at the PD score of the subset, you just look at those splits which separate at least two elements in the given subset. So the subset now could be the red vertices of the graph, because the underlying set is now the vertex set of our graph. And this is exactly the set of edges that are, yeah, what's called covered in the graph. So this means there's one endpoint of the edge in the set. And if you work out the details, I mean, it's not really hard, it's more like an observation, then this gives you a reduction from this known NP-hard problem minimum vertex cover. And this is the very basic way to get hardness for this kind of PD optimization problem on split systems, and you can just try to find other problems that are related to this and get other hardness results as well. Okay, so now that the general thing is hard, it's natural to look at those things that might not be hard, and we already know that for some simple structured split system, it's not hard. For example, as Charles mentioned, if they all fit on a tree, if all the splits fit on a tree, what's usually called a compatible split system, then we can do it. And he already mentioned that the simple greedy strategy would work, which is just taking, if you want to select, say, 4 elements, you just start with 2 which are furthest apart in the tree, which is in this case x5 and x9, and then you select the next one, which is the green, circled green thing, which is x1. And you select this one because if you look at the path that connects the taxon, or the leaf, with the red path, then this green path is as long as possible among all the taxons which have not been selected yet. And then you go on with this, and the next you would select this, the blue circled x8, because this gives you the biggest additional contribution to the path length, or the length of the tree you've built so far. So this works. And what this essentially gives you, you can see, is a partition of the underlying tree into paths. And what you're actually interested in is the length of these paths. This is the most important quantity. I mean, no, you're not actually interested in the paths itself. It's just about the length, because these lengths and the sum of them forms the PD score. And there is actually a very efficient implementation of this greedy strategy given in 2006 by Min and al. And it's almost linear and depends only by a log k factor on the number of tags that you would like to select. And yeah, it's a nice theoretical result, maybe not very, it doesn't have much impact in practice, at least not if the data set is not really huge. But it's interesting to see that actually you can implement the whole greedy thing in such a way that it does not, that the running time does not depend on the number of tags that you would like to select, which is kind of interesting, at least for us in the end, when we saw it. And the basic idea is, as I said on a previous slide, you've seen that you're interested in this kind of path decomposition of the tree. And the basic insight is that you can compute this path decomposition in linear time in a recursive fashion. Once you have these paths, and then of course its lengths, their lengths, then you just, if you want to select k taxa such that the PD score is maximized, you just need to select the k longest paths. And this is just, you have n numbers, and you would like to select the k, the k biggest among them. And this is this kind of selection problem, which is known for a long time to be solvable in linear time. So it really boils down to computing this path decomposition, and this can be done recursively. If you root the whole tree on some leaf, this has no biological meaning, it's just for computing purposes. Then you can see, if you want to know what is the leaf that is furthest away from you, then you can look at these subtrees, and if you've already solved the problem to find the leaf that's furthest away from all these guys, then you just know, oh yeah, the longest thing from you to some leaf is just an extension of one of these, and so you can just compute it recursively, and if you implement it carefully, there's no problem, and you get a linear running time. So for compatible things, it was already known, and we've just speed up the thing, and along the same lines, we've done with a slightly more general type of split system, which is called a circular split systems. And those circular split systems, most of you might have been come in contact with via the neighbor net algorithm, for example, because the output normally gives you kind of circular split systems. Split system represented by such a split network, as we've seen before, where all the taxons are on the outside of the network, and they can be connected in a graph theoretic sense by a cycle around the whole network. And for this type of split systems, Min et al. In 2007 gave an algorithm, which is again polynomial time, kn cubed to be more precise, and we found a way to speed up the thing by a factor of n squared, more or less. And this now, I think, can really have an impact if you would like to look at big data sets, because if you have something like kn or kn cubed, makes probably a big difference. Okay, and I just want to give you an idea how we could speed up the thing. And it came a little bit as a surprise because we took a detour into geometry, or at least into geometrical arguments. And the first step towards that is to look at the split system not in terms of the network, but go back to the representation where the name comes from, circular split system. You can arrange the taxon or represent the taxons by points which are arranged on the boundary of a cycle or a circle in the plane. So you just arrange them around. Really, it's now a circle. I mean, in the projection it's probably not, but yeah, it should be a circle. You have those taxons on the circle, and you represent the splits by lines, which just split one half of the circle versus the rest. And doing this, you can now look what would be the PD score of this four-element subset, and then you realize, oh yeah, that's more or less the perimeter of the inscribed convex polygon, in this case, inscribed convex quadrangle. Now, the distance between two taxons is not the Euclidean distance, of course, although the points are now really points in the plane. It's the distance induced by the weights of our split system, so it's just the sum of the weights of those splits which separate x7 and x9. But this distance, although it's not the Euclidean distance, shares an important property with the Euclidean distance. So there have been techniques developed a long time ago for actually computing inscribed convex polygons with number k of vertices of maximum Euclidean perimeter. And if you look carefully what the crucial properties are those algorithms and their efficiency relies on, then you realize, oh yeah, you have the same properties also for your distance induced by this weighted split system. And that's what we used. And to give you a visual impression where the efficiency comes from, this is this kind of interleaving property. This was observed for the Euclidean distance back in 85, so more than 20 years ago. And it says, okay, if you already have computed, say, a solution of size 5, which is, say, rooted at this taxon, so all the solution for the moment should contain the purple vertex up there. The technical details are somewhat involved, but just to give you a glimpse of what it is about. So, and then this red thing should be an optimal one among those containing the purple taxon. And then you would like to add another taxon. And what you then know is that the first of these additional ones must lie in this part of the circle. Another one, the next one must lie inside here. So you get this kind of interleaving pattern. And this is where the efficiency comes from. And it was very interesting for us to see. And as I said before, you get something like kn plus n log n, which is a, well, good speed up over the known algorithm, I guess. Okay, so let me just briefly summarize what we've done. We've explored a little bit how the structure of the underlying split system influences whether or not you can solve these PD optimization problem efficiently. For some of these split systems, it's hard, and please note that the structure of these split systems is rather simple. I mean, this split system derived from a graph is just all splits 2 versus the rest. It's a very simply structured split system, and it already gives you NP hardness. And depending on what else you want to show, you might add a little bit more structure. And as we've seen also this tree problem, if you have split systems which come from more than 3 trees, the union of at least 3 compatible split systems, already there it's again NP hard. So for very simply structured split system, it's hard. But on the other hand, by some connections we discovered to problems studied, say, for example, in computational geometry, we were able to come up with very efficient algorithms for split systems that are relevant in biology. The compatible ones, which was known, we just gave a slight speed up, and those circular ones where we had a good speed up. Okay, so thank you for your attention.
A quick question?
So the problem where we had reduction from vertex cover, is it equivalent to vertex cover or is it harder? Because vertex cover have many nice properties.
It is harder because you could also reduce the hitting set problem in its full generality to it. So in some sense it's a little bit harder.